So what I'm going to do is, as I said, take a few simple problems, which will help you with your homework assignment. So this is a summary sheet for Mosfet. Right, so here we have the structure of the Mosfet here. This is the top view of the Mosfet here, what we mean by LS, LD, LW and all that here. These are the, most of the time when we look at Mosfet, we look at it Mosfet biased above threshold when it's conducting. And in that case, if it's in the linear region, this is the expression for current. If it is in the saturation region, this is the expression for current. And in all these expressions, in order to calculate currents, you need the threshold voltage. So threshold voltage is in general a function of source to body. So if the source to body voltage happens to be 0, then it's fine. You can simply take whatever VTH and 0 parameter is given to you. Otherwise, you need to calculate the threshold voltage here. The other parameter is beta N and beta P, depending on NOP. That depends on the Kp, transconductance parameter, multiplied by W by L. And Kp again will be given to you. W and L normally you have to determine as part of the problem. It either is given in the problem or you determine it. I've written here W effective and L effective. The reason is, when you draw a channel length like this, as a designer, when you specify that so in your layout, you specify, let's say, L equal to 1 micron. Now what happens is, even though you specify L equal to 1 micron, you don't end up getting 1 micron. If you look at it here, this particular picture, this N plus little bit extends under the gate here, and this side also extends under the gate here. So effective channel length, L effective, is L minus twice of what we call as LD, those extension region. So what I've given here is some typical parameters for a 0.5 micron geometry here. So what happens is, because of this extension here, the L effective is not simply L, it's L. L minus 2 times this LD here. For this particular technology, the LD happens to be sort of negligible, so we won't take it here. Similarly, W effective, even though, let's say, you've drawn 2 micron, you don't end up getting 2 micron. You again end up getting W effective is W minus twice of WD. Where's WD here? Here, this one here. All right. So the effective width and the effective L, which go into your electrical model, are not the same as geometrical L and geometrical W. They're a little bit smaller here. And so we need to calculate. But in our simplified analysis, at least for tutorials and exams, most of the time, whatever W is given, you take that as W effective. Whatever L is given, you take that as L effective. All right. But in real life, you'll have to take these things into account. All right. So that's the model for transistor when it is biased above threshold. So these are the expressions. These are the small signal parameters here. The small signal model is given here. So small signal, how do you calculate GM? So of course, small signal parameters depend on the bias. So once you know the bias here, GM can be calculated either this expression, 2IDSQ by VGSQ minus VTHN, or sometimes this is convenient, simply square root 2IDSQ times beta here. So either one of them is there. R0 is 1 over lambda times IDSQ. GMB, body transconductance, is GM times eta. Eta can be calculated using this expression here. So that's the small signal model here. And if you want to do high frequency analysis, then all the capacitances are here. Capacitances are given here, and the typical parameters are also specified for a 0.5 micron geometry. All right, so that's the summary sheet. These are the things that you're expected to know well in order to do circuit analysis here. In saturation region, anyway, I think this part is given here, so that's fine. All right, so let's take up the first problem. We'll start from very simple problems. So the first simple problem is, note that the simplified parameters are given. In these simplified parameters, our NMOS and PMOS are symmetrical. Kp for N and Kp for P is the same. VTHN0 is minus VTH0 is 1 volt here. Lambda. So we've taken all, just to keep things simple here, we've given you the values of all the capacitors here. Fine. And this is the body parameter here. Gamma, if you go back and look at gamma, is required to calculate the threshold voltage here, in case the source to body voltage is not 0. Anyway, all right, so let's look at this particular problem. Simple case where we are given a MOSFET N-type with a resistor 80K, voltage is 3.3, and we are asked to calculate the drain current and drain to source voltage here. And so whenever we don't mention in the tutorials and exams, please don't ask. If nothing is mentioned, take VBS equal to 0. Body is shorted to source. Unless we explicitly say take body, the body is not connected to source, or take body effect into account, just assume VBS equal to 0. All right, so even for this very simple case, the first thing that we note here, keep in mind, when you see a circuit like this and you see 1.5 volts, the first thing to figure out is my transistor on? Is it biased above threshold or not? Right? So is it biased above threshold or not? And so 1.5 volts is VGS. And so we go and look at the threshold voltage. Threshold voltage for NMOS is 1 volt. And so 1.5 is greater than 1 volt. So I know the transistor is biased above threshold. Right? So it's conducting. If for example, I put here 0.5 volt, then 0.5 volt VGS is 0.5 and VT is 1. So the transistor is in subthreshold and in considerably below threshold. And therefore, we would take the transistor to be practically non-conducting. We'll say the current is negligible here. So if I had put here 0.5 volt here, you would have then said current through this is negligible, and therefore the output voltage would be practically, this drain voltage would be practically equal to 3.3. If you want to accurately calculate what is this particular voltage here more accurate, then I need a model for below threshold. I need a model for below threshold. That's a exponential, current varies exponentially with voltage here. And one could use that to calculate the current values here, and then a more precise value. But most of the time it's not necessary. Once you're much below threshold, the currents are very small, and the voltages are would be 3.3. Anyway, so here VGS is greater than VTN. So we know transistor is conducting. Now we have the following problem. Is my transistor, if you go and look at once it's conducting, is it in linear or saturation? So I have this problem. Is it in linear or saturation? It could be linear. It could be in saturation. Just like in a bipolar, it could be an active region or saturation region. Similarly, here it could be linear or saturation region. So simply by looking at the circuit, I can't tell. All right. So the thing is, let's say we assume saturation. We assume that the transistor is in saturation region. For the saturation region, we have this expression for current. And basically we have everything. Beta, note that to calculate beta is Kp. Kp is given here. And W by L is also given, 2 by 1. So you can calculate beta. Right? And VTH and we know, VGS we know. So there. And the accurate expression says that there is a 1 plus lambda times VDS here. But please note the value of lambda. Lambda is 0.01. So 0.01 multiplied by VDS. VDS would be what? At the most it can be 3. So VDS 0.01 multiplied by 3. So we are talking about 0.03. Right? So we are talking about 1 plus 0.03. We are talking about 3%. So we're not going to bother about it. In our quick calculations and all that, we'll not bother about 1 plus lambda. We'll neglect it in the DC calculations here. So that's why I put an approximate sign because I've neglected this. So the IDS comes out to be 25 microamperes. It's straightforward substitution of voltages and sizes and all that gives us 25 microamperes. Now, the problem doesn't stop here because I've assumed saturation. I have to check whether it's really in saturation region here. So I calculate VDS. So I calculate VDS is VDD minus IDS RD and I get 1.3 volt. All right, so I get 1.3 volt. Then how do I check? Well, I calculate VD sat, the saturation voltage. When does saturation begin in a MOSFET? The edge of saturation is VD sat, which is VGS minus VTN. So this information is given. So that's 0.5 and 1.3 is greater than 0.5. So the transistor is in saturation region. My assumption is correct and my current values and voltages are all fine. So in this case, it turns out to be the assumption was correct and everything turned out to be fine. And I've calculated the current and I've calculated the voltage that is there. But suppose I just very quickly modify the problem. Instead of 1.5, I apply 2 volt. So now 2 volt, you would expect more current would flow. And more current would flow means more drop would occur here, which means less drop here. And less drop here, which means it may go into linear region here. So let's do that. Again, if I assume saturation region, now the current, if I assume saturation region says 100 microamperes. If I calculate VDS, it says minus 4.7. Obviously, then my assumption is incorrect. And the transistor has to be obviously in linear region here. Now in linear region, it's a little bit more complex. Linear region expression is here. IDS is beta n, VGS minus VTH, and VDS minus VDS squared by 2. Fine, so there is a VDS also. Saturation makes things simpler because there is no VDS there. Right? This term, as we said, is sort of negligible. So there is a VDS also here. Now the other equation is, so this I have, VDS is VDD minus IDS RD. That's the VDS part here. VDD minus IDS RD. So we have these two equations and we need to solve. It becomes a quadratic equation and we need to solve. And if you do that, I'm not going to go through this. So you get 38.55 and VDS is 0.216 here. So that's the value that you end up getting here. So calculations in linear region become a little bit tedious because of a quadratic. Now, many times what happens is when you are in the linear region, the VDS is often, many times it can go to a small value. And what may happen is VDS is small, so this quadratic term may be negligible. VDS squared by 2 may be sort of negligible. And so if you want to do a quick calculation, what you can do is, in some cases, you can assume that this is negligible and then solve these two equations to obtain a value of VDS. And then you can check whether the second term is indeed negligible compared with that. If it's there, then it's fine. Your calculation is okay. If not, well, then you have to do a quadratic solution. All right, fine. So let's take the next problem here. So in the previous problems, all the information was given 2 by 1, 2 volt, everything is given and you're asked to figure it out. In the next case, it's slightly more like a, a sort of a design problem. Let's say, determine a suitable value of V bias such that IDS is equal to 30 microamperes. All right, so for some reason, I want this transistor to be biased at 30 microamperes and I want to determine what is V bias. Now, normally, the problem would be not as simplified as this. It would be that, let's say you want it to be, okay, we'll come to that. You want it to be biased at 30 microamperes. And you have to figure out what is the V bias and what is the size also. Because who's going to give you size? Right? You are supposed to determine the size of the transistor and you are supposed to determine the bias. These are the two things, So once you have the structure of a circuit, let's say this is the circuit, let's say this is an amplifier or an inverter or whatever it is. And if you have to design it, once you get the structure, then designing means, of course, you'll have to find out what is the value of the resistor. And as far as MOS is concerned, you have to find out what is the size and what is the bias that I have to apply. Right? So these are the two things that you need to determine in a MOSFET, the bias and the size. Right? And all right. So in this case, determine a suitable value of V bias such that IDS is 30 microamperes. All right, so in this case, note that the first thing that I do always is when size is given, I determine beta because I need it in all my equations. So Kp and W by L, so determine that here. Well, let's say I don't know whether with 30 microamperes I can bias it in saturation or not, but let's say I assume saturation. So if I assume saturation, 30 microamperes is given here. IDS beta n by 2 VGS minus VTH is 30 microamperes here. And from there, I determine VGS. VGS is 1.346. So which is the V bias here. The next thing is, because 30 microamperes is given, so I determine what is the drain to source voltage here. And drain to source voltage is 0.9 volt with 30 microamperes and 80K known. So VDS is 0.9. And note that the saturation voltage, which is VGS minus VTN. So that's 0.346. So that's 0.9 volt greater than 0.346. So the transistor is in saturation region. And therefore, it turns out to be fine. I've been able to bias my transistor at 30 microamperes current by simply choosing V bias equal to 1.346. And the transistor is in saturation. The next one is more interesting. It says, determine a suitable value of VGS and the size of a MOSFET such that IDS is 38 microamperes and transistor is biased in saturation. That's all the problem says. Why? Because let's say I need to make an amplifier. In an amplifier, the transistor has to be biased in saturation region. And so that's the requirement that's coming from, that it should bias in saturation region. And let's say from somewhere, the requirement comes that I need to bias it at 38 microamperes. Now, what do I have to determine? The V bias and the W by L. So for the saturation region, these are the equations that are there here. IDS is here. You can take this equation, rewrite it in terms of VGS and VD sat. can be written as VGS minus VTHN, or it can also be written as square root 2 IDS by beta. Different forms are convenient at different times here. All right, so how do we do it? Well, since we are given that the MOSFET has to be biased in saturation region and the current is also given, so we can calculate what is the VDS here. The VDS is 0.26. So that's 0.26 here. And because it's in saturation region, it has to be greater than VDSat, so which is VGS minus VTN, or also equal to square root 2 IDS by beta. Fine, you can VDSat, note that you can write it as in this form, or you can write it in terms of current, square root 2 IDS by beta here. So now the issue is, so I have to ensure that this VDS is larger than this particular term. Right now, IDS is, so the issue is, now it's up to us. How much larger do we want it to be? That information is not given. So note, this is the transistor characteristics. This is the linear region, and this is the saturation region here. So what is given in the problem is 0.26 here. Let's say this is 0.26. So the transistor has to be in saturation region. We have to decide what is the drain to source saturation voltage here. So we really want it to be, obviously I don't want it to be right here. If somebody is saying bias the transistor in saturation region, I'm not going to place it at the edge of the saturation, because then, of course, a little bit of error here and there is going to push it maybe into linear and all that. So I have to keep some margin, right? So now this is where subjectivity comes. How much margin do you want to put? So in this case, suppose we have set 0.26 and I keep VDSat as 0.1. Obviously, it's a design problem, so you will get multiple answers depending on the choice that you make here. Somebody may take it as 0.05 or whatever, depending on. So suppose I choose this VDSat as 0.1. And if I choose this as 0.1, then VDS 0.26 is obviously greater than 0.1, and I'm there in saturation region. Once I'm given this 0.1, then of course, you know that you need to bias it at 0.9 volt. VGS minus VTN is 0.1. And, I need to bias it at 1.1 because VTN is 1 volt here. So I need to bias it at 1.1 volt. And also note that because 2 IDS by beta and IDS is given to you, and so I get beta n is Kp and W by L, so I get W by L is about 76 or so. I've put greater than if you want it even smaller than 0.1. So W by L size you need to get around 76 or so. Now, you have to further determine what is the L and what is W. Now, in this case, if we are talking about that the minimum channel length, let's say allowed by my technology is 1 micron. So I won't unnecessarily choose a larger transistor. If the minimum L allowed by a technology is, let's say 1, so let's go ahead and choose L equal to 1, and then W becomes 76 micron. So that sort of completes the design. You know what is W, what is L, and what is the bias that you have to apply in order to obtain 38 microamperes current and biased in saturation region. All right. Okay. Let's look at this one. So here, as I said, a series of simple circuits. Let's start with this. So here is a MOSFET connected with gate and drain shorted together with the resistor put here, and we are asked to calculate again the currents and so if once you know the current, of course you know the voltage here. Now, anybody sees a problem here? First thing, normally, where is the, so although I've not said it in this particular problem, where is the body normally connected? Body of an NMOS is connected to the most negative point in the circuit. The most negative point in the circuit is ground. So the body is connected to ground, and where is the source? Obviously is not at ground. So I have a source to body voltage. I have a source to body voltage, and which means that the threshold voltage of this transistor is not going to be simply VTHN 0. 1 volt here. Threshold voltage is going to be depending on this expression here. This expression that you see here, this is what we'll decide here. Alright, the first thing is, whenever you see gate and drain shorted together, the first thing that you know is that it's biased in saturation. Gate and drain shorted together, so if you look at it, VDS is equal to VGS. When you short the gate to drain, VDS equal to VGS, and obviously VDS is greater than VGS minus VTN. So the transistor is in saturation region. With gate drain shorted together, the first thing is out, that the transistor is in saturation region. So I can use this expression for current. Now, what I don't know is what is this VTHN in this case, because it is the source and the body are at a different point here. So VGS is also I don't know VGS directly. So VGS is VDD I know, minus this voltage here, source voltage, which is IDS-RD. So that's another expression for current that I get. And the other one that I have is VTHN is VTHN0 plus gamma square root 2 phi f plus VSB minus this here. So 2 phi f is given to you, 0.7. Gamma is called the body parameter because of, so this is 0.7 here. So all these things are given to you, VTHN0 here, but you need to determine the source to body voltage here. And source to body voltage here, note that the source is simply this point here. So source to body voltage is IDS-RD. Body is connected to ground and source is IDS-RD, so this is here. So now I have this equation, and this equation. I need to solve them up, and so it may require, so the final answers are here. IDS is 18 microamperes, VS is 1.438, and note that VTHN is also comes out to be 1.438. So interestingly, note that although the VTHN of a transistor without the body bias is 1 volt, when you put it in a circuit like this, its threshold voltage becomes higher because the source body voltage is reverse bias, so it becomes higher. Anyway, so now to figure this out, well, you may use, you may start by assuming source to body voltage is 0 and use some value of VTHN here, and using these two equations, find out what is the current and what is VGS, and then you'll get the value of source to body voltage, then update this value here, 2-3 iterations, and you may go ahead and figure this out, IDS and VTHN, all right? So in these cases, don't try to write one big equation. Better is to use an iterative method, and they don't take too much time to converge. Okay, there's a square root and all that, so 2-3 iterations will help you get the final value here. All right, example 6. So we have, so far we've been doing NMOS, so let me introduce a PMOS here. So we have a PMOS here. All these, right now all these circuits are arbitrary for us. The goal is just to learn how to do some simple analysis, okay? So here is another circuit. So we have a PMOS, and it's given here. In PMOS, almost all the time, the source and body are shorted together. In PMOS here, right? So source and body are shorted together. VSB is 2. So we have a PMOS here. We can calculate its beta. It will be Kp. Kp is both same, 5/1 here. Similarly, we can calculate beta of this particular one. So again, to calculate this, let's assume we know that the NMOS is in saturation region. NMOS is in saturation region. We don't know what the voltage is here at this point, so we cannot calculate the current here. But if we go and look at this one, well, if we assume, let's say M2 is in saturation region, then the expression for current for a PMOS, now note that in a PMOS current flows from source to drain, so I have ISD, beta P/2, VSG, we talk in terms of source to gate instead of gate to source, plus, we put a plus here, VTHP, which is negative. VTHP is negative here. And if we use that, if we assume it to be in saturation region, we get 62.5 microamperes. Now, we need to check, is it really in saturation region? So for that, I need to calculate what is VSD, saturation. What is the voltage required to keep it in saturation region? So earlier it was VGS minus VTN. Now it is VSG plus VTHP or square root 2 ISD by beta. So we calculate this to be 0.5. So we need this much voltage for it to be, this drop from here to here should be at least 0.5 for our assumption to be correct. All right, so let's go forward. So this is the current 62.5. This must flow through this transistor also. So we can calculate the gate to source voltage here. So if I look at this transistor, IDS is beta n by 2 VGS minus VTHN square. Same current flow 62.5. I can calculate what is the gate to source voltage here, which comes out to be 2.2. So the voltage at this node is 2.2. And therefore the drop from here to here is 3.3 minus 2.2 is 1.1. And that happens to be greater than 0.5. So everything is fine. We've determined the currents and determined all the relevant information that we want. At this point, if let's say, if we had found this difference to be less than 0.5, then of course we have to go back and assume it to be in the linear region, and write an expression for linear region. This remains in the saturation region, and then solve the two. You'll get equation for linear region, equation for saturation region, solve them together, and find out what the values are. So note that it's straightforward, except that you have to become familiar with these equations. Equation for a PMOS, saturation voltage for a PMOS, equation for an NMOS, saturation voltage for an NMOS. Otherwise, is the same circuit analysis that you've done many times here. All right, this is interesting. Which mode are the two transistors? So we know that you're seeing from all these examples that I have to know in which mode is my transistor working in. Is it in linear? Is it in saturation region? I have to know that, right? So here is a circuit. Yeah.
So I'm using the same VSD sat for both?
No. This is obviously in saturation region. A gate and drain are shorted together. So this is in saturation region. So I calculated the voltage at this node, which is 2.2. And this is 3.3. So 3.3 minus 2.2 is 1.1. And we are comparing it with the saturation voltage here, which is 0.5. So it's greater than 0.5. So it's indeed in saturation. All right. Let's look at this one. Which mode are the two transistors operating in? First of all, look at these two. Are the transistors biased above threshold? Will they be conducting or not? Right? Everybody agrees it will be conducting? 1.5 here. VGS is what? 1.5 greater than threshold voltage, which is 1 volt. VSG is what? 3.3 minus 1.3. So that's also greater than the threshold voltage. Right? So both of them are biased above threshold. Both of them are conducting. Now, are they in saturation? Are they in linear? What is really going on? How do I determine? Body is shorted together. Body of this is shorted together. Body of PMOSs are always shorted together with the source. Okay, so don't worry about it. And NMOS body will connect to the ground here. So source to body is again 0. So is it in saturation region or is it in linear region? So I mean, simply looking at the circuit, I can't tell, right? Unless you've solved the circuit before, you can't tell. So you have to make an assumption. And what is the assumption that you can make? Well, it requires less of a calculation. If you have noticed, it requires less of a calculation with saturation region, right? Because the VDS term is missing. So we assume that it's in saturation region. If our luck is right, well, it will come out to be in saturation, and that's the end of the story. But if it is not in saturation region, then we'll do a slightly messier analysis with linear region, right? So let's assume it to be in saturation. Let's assume both of them are in saturation. So M2 in saturation region, then the current flowing through M2 would have been ISD will be beta P by 2 VSG plus VTHP square 122.5 microamperes. All right. Let's do the M1 also in saturation region. IDS is beta N by 2 VGS minus VTHN square 25 microamperes. All right. Now what shall we do? They are in series, so current has to be the same. So now what do you say? Which one is wrong? Both may be wrong, but which one you can immediately say is wrong? Immediately you can say one of them is wrong. Is this one wrong? Or is this one wrong? One of them, as I said, I'm 100% sure is wrong. And one can point out which one. See, that's where you have to understand the device. So M2 is wrong. M2 is wrong. M2 cannot be in saturation region. M1 could be. M1 could be. Why am I saying this? Note that once you fix the source to gate voltage is fixed, right? Once you fix the source to gate voltage, and if a transistor is in saturation region, it has to note this is the saturation region, right? And the current that flows in the saturation region depends on what? Source to gate voltage. So if you say it is in saturation region, source to gate voltage is fixed, it has to carry 122. Fine. Similarly, and that's the maximum current that a transistor can carry once its source to gate voltage is fixed. Note that this entire graph is for a constant gate to source for an N-type or for a source to gate for a P-type. The source to gate voltage is constant. So the maximum current for a given source to gate voltage or a gate to source voltage, the maximum current that a transistor can carry is the current in saturation region here. So if it were in saturation region, it needs 122.5. Now, what is the maximum current that M1 can allow? That also is in saturation region, allow 25. So there's no way that 122.5 can flow through this. It's not possible. There's no way it is possible that this would allow it. So which means that M2 cannot be in saturation. If it were in saturation region, it would require 122.5. And that's simply not possible because the maximum current that M1 can allow is only 25. So M2 cannot be in saturation region. I can immediately cross it out and say M2 has to be in linear. Now, M1 I still don't know. M1 could also be in linear region. I don't know yet. Okay, so but M2 is definitely not in saturation region here. So M2 cannot be in saturation region. So what we do is now M2 in linear region. Now I'm again assuming that M1 is in saturation region though. So if M1 is in saturation region, it requires a current of 25 microamperes. Note something interesting about a saturation region. In a saturation region, the current depends only on the gate to source voltage. It doesn't matter what the voltage of the drain is. Right? It doesn't matter what the voltage of the drain is. It only depends on gate to source. So if I assume M1 is in saturation region, I know the current flowing through my system has to be 25 microamperes. Right? So that's what we do. We say M2 is in linear, but M1 is in saturation region. So the current has to be 25 microamperes. And current in linear region is beta P VSG plus VTHP VSD minus 0.5 VSD squared. Right? So we know all of that. We know beta P, we know VSG, we know VTHP. The only unknown is VSD. Right? So again, what you can do is, you can assume that the quadratic term is sort of negligible. You can assume it to be negligible. And if you assume it to be negligible, very quickly you can calculate VSD. And then you can take VSD square and all that and check whether the assumption is correct or not. So if I do that, I obtain VSD is 0.05. So obviously, if VSD is 0.05, this term will be even smaller. You can forget about it. So this is fine, 0.05. So VSD2 is 0.05. Now I need to still check is M1 in saturation or not. So now what do? I calculate this VSD VDS1. For it to be in saturation region, VDS1 must be greater than 0.5. Why? Because this is VGS. What is the saturation voltage here? VGS minus VT. So that's 0.5. So the drop from here to here must be greater than 0.5. So how do I get this drop? Well, I've already calculated the drop here. So I know that 3.3 minus 0.05. So that's a very large voltage here. Obviously, it's greater than 0.5. So things are fine. So what happens is in this case, M2 is in linear region. M1 is indeed in saturation region. And we have found out the current 25 microamperes. And we have also found out what is the drop here and what is the voltage at this particular node. Okay. So it's very hard to bias two transistors connected in series. You can see here, if two transistors are connected in series and you want both of them in saturation region, you'll have to match the current exactly. That becomes very hard. So invariably what would happen is one transistor would go into linear and one would remain in maybe saturation. So all right, so let's move forward and let's look at this one. So what we want is a plot of V out versus V in. And we also want what is the maximum small signal gain that I can get from this particular circuit here. Small signal gain meaning that, we are changing V in. So we are changing the bias of this particular MOSFET here. And small signal gain means in addition to V in, I'll attach a small sinusoidal source. So I will get let's say a small signal voltage here, and the ratio of the two small signal voltages will give us the gain. All right. Another way of saying it is gain is the derivative of V out versus V in. Any change in V out divided by change in V in, that's the small signal gain. Right. So this is what I want. And why is this circuit of interest? Because this is one of the simplest inverters that you can form, a digital inverter. You'll see in a minute why. All right. So let's see if we can plot this out. So to plot it out, let's draw the axis V in, V out. All right. So what will happen now? We are starting V in from 0 and we'll go up to 3.3. Our power supply is 3.3, so we want to go from 0 to 3.3. So what will happen now? It's the same MOSFET that we've been talking about. Same simplified parameters here. So what will happen now? How will the characteristics go? Vin is 0. Vin is 0. The input voltage is less than threshold voltage. Transistor is off. The output voltage is 3.3. So output voltage is 3.3. It will remain 3.3 till, everybody sees here, till it will remain 3.3 because the current will be very small, till about the threshold voltage. Right? This is a simplified view. Obviously, as I start approaching threshold voltage, current will start flowing and this will not be absolutely flat. All right. So this is a simplified view here. So this we get here. Now, suppose after VTN is 1 volt. So this will be 1 volt here. Let's say I apply 1.1. If I apply 1.1, current will flow, Vout will start dropping. Right? Everybody sees Vout will start dropping. Okay. Will start dropping, and let me draw it like this here. Okay. Let me draw it out like this. Now, once the transistor starts conducting, it could be in saturation or it could be in linear. So, once I apply 1.1 here, where do you think, just to the right of it, where do you think it is in? Linear or saturation? Where will it be? Why saturation? Not current is less, yes, okay. So note that just above threshold voltage, current is still going to be small. So what will be the value of this voltage? Close to 3.3. And what is the saturation voltage required if I apply 1.1? 0.1, and the voltage here is 3 or so. So obviously it goes into saturation region. So immediately once you cross this, it goes into saturation region, right? And at some point, if you keep on increasing it, current will keep on falling and this voltage will become small. So at some point, it will go into linear region, right? So this is what we'll find here. Here is sort of cut off. Here will be somewhere saturation region, and then it will go into linear region. That's how your, when you plot V in versus V out, it will go here. Will this ever go to 0? Will it ever go to 0? It will never go to 0, right? I mean, if you keep on doing, what will happen? I mean, the voltage will keep on dropping, but, you know, it will remain more because there's some drop will always occur across 80K. Transistor is on, so some drop will always occur across 80K. So it will never go to 0 anyway. Oh, we'll see that later on. Okay, so this is how it is going here. All right, so we have found, is it possible to find out this crossing point? When does it go from saturation to linear? Now, why am I interested in this? Note that I want to find the maximum gain. Where will the maximum gain occur here? Maximum gain will occur if it is in saturation region. You agree? In saturation region, note, in saturation region, the MOSFET acts like a current source. And gain, you know, if you want to build an amplifier and all that, you need a transistor biased in active region. Active region for a MOSFET is saturation. So the gain would be maximum somewhere in this region. The gain will not be. You can also see from the slopes, right? Gain is also change in the slope, dV out by dV in. So you can see here the gain is small here, and the gain is increasing, and the gain is again decreasing, right? So somewhere maybe there's a maximum gain, right? And so how do I calculate the maximum gain? So the MOSFET, a small signal model, if I look at it, is this here. Because body is not important, body is shorted to source, so I've not shown body. Between gate and source, there's nothing. We are talking about low frequency case here. This is GM-VGS, and between here and here, there's R0. So the gain of this particular amp, this circuit here would be, R0 will come in parallel, we all know that, will come in parallel with 80K. R0 is usually very large compared to this, so gain is equal to minus GMRD. Just like a bipolar, it used to be, gain used to be equal to minus GMRC. So here it is minus GMRD. So when would gain be maximum? Gain would be maximum where GM is maximum, because RD is constant. And what is GM? Well, one way of writing GM is square root 2 IDS beta. Verify that one way of writing GM is, we have given you expressions earlier, GM is square root 2 IDS beta into RD. So where would gain be maximum? Where GM is maximum. Where would GM be maximum? Where IDS is maximum. So where do you think IDS is maximum? But it has to be in saturation region. So are you seeing that as I'm increasing the value of V in, IDS is continuously increasing because the gate to source voltage is increasing? So IDS is continuously increasing. But as I keep on increasing, a stage comes, so IDS is completely increasing, but a stage comes where it goes into linear. So where is my transistor, where that is biased in saturation region, but it has the maximum drain to source current at the same time? It is here. It is in at the edge here. It is still in saturation region, but it has the highest current. Because beyond that, I have higher current, but it's no longer in saturation region. Before this, it is in saturation region, but it has lesser current. So what I'm looking for is this boundary. What is this boundary between saturation and linear? Where is this boundary occurring? And once I can find this boundary here, then this voltage I can find. Then once I know the voltage, I know the current, and I'll know this transconductance, and I'll know the gain and everything. Okay, so let's do that here. So boundary will occur where? Boundary will occur when the transistor is at the edge of saturation region, right? So note, does it make sense? I don't know what voltage do I have to apply, so let's say this is V in. And at the edge of saturation means the drain to source voltage is VD sat. And what is VD sat? V in minus VTN. Because V in is nothing but VGS. VGS minus VTN is VD sat. So we know that V out is equal to V in minus VTN. So this is the thing that we have. So once we recognize this situation here, we can write IDS is beta n by 2 V in minus VTHN. Somewhere you'll see VTN, somewhere you'll see VTHN. These are the same here. V out is V in minus, we have written here V in minus VTN, which is also equal to VDD minus IDS RD. And we need to solve these together. I'm not going to go through that. So we find V in is 1.58, V out is 0.61, IDS is 33.64. Once you solve these two equations together, you get the value. You get the value where you're at the borderline of borderline of saturation and linear region. You get these values here. And once I get IDS, I can get GM and I can get AV. So maximum gain that I can get is minus 9.28. All right, as usual, what you can do is, if you want, if you're not confident about your analysis, you can always go ahead and simulate and see what is happening here. So these are simulation results. Note that it's constant right up to about 1 volt or so, starts falling, and then eventually keeps on going to smaller and smaller values here, right? And if I take the derivative, I'll get the gain. So note that gain keeps on increasing till it reaches that particular point here. After that, gain collapses suddenly. Why? Because it enters into linear region. So gain collapses here, it comes back here. And the maximum gain from simulation is 9.152, which is 1.57. These are, instead of 1.57, these are all very close here. All right, so, okay. So that's how you end up calculating that. All right, what about this? What will happen? So let's understand this. I have a MOSFET here, biased at 3.3 volt, and there's a switch here, and there's a capacitance of 1 PF. And the capacitance is also initially charged to 3.3. At time t equal to 0, I close the switch. What will happen to this capacitor? Suppose I ask, how much time will it take to discharge? Will it completely discharge? Will it go to 0? Or how will it, let's look at how will it discharge? I close the switch, right? What will happen? By the way, this is interesting. Before you open the switch, this is 3.3, this is 0. And the switch is open. The transistor is on and no current is flowing. Is that possible? Transistor is on and no current is flowing. Switch is open. VGS is greater than VTN. Right? Is that possible? A transistor being on and no current flowing. Well, you go back and see here. Somewhere I'll have a characteristics of a transistor. Yeah. This, I said the whole graph is for a VGS, a constant VGS. Right? So VGS can be above threshold voltage, but no current is flowing. Where is the transistor biased? If no current is flowing? Right here. Right here at this particular point here, right? Transistor is on. Note that transistor is on. VGS is larger than VTN, but no current is flowing. Right? Okay, all right. So let's get back to that. So what happens now? So note that the moment I close the switch, this is 3.3, and this is also 3.3. The transistor now, has a path for conducting current. The capacitor will start to discharge. Is the transistor in linear or saturation region? Saturation region, right? So VD sat, of course, is 2.3. It starts off with 3.3. So once it is in saturation region, note that this is the characteristics. The current is constant. Gate to source voltage is 3.3. So let's say the whole graph is for 3.3. So the current is constant. So there's a constant current which flows here, which discharges the capacitors. But as it keeps on discharging, this 3.3 will go to 3, and then eventually it will arrive at 2.3. Now, as it falls below 2.3, what will happen? So this is 2.3 for us. As it falls below 2.3, the transistor enters into linear region. And linear region, and now, the current will, of course, depend on what is VDS and starts to drop. And then eventually discharges. Okay. So this is how you can see here the transistor is, the capacitor is discharging. It goes here, 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 and all that. Note that the current which is discharging is initially constant, and then the current keeps on dropping. All right, so so this is fine. It drops here, and if you leave it for long enough time, it will drop to as close to 0 as you want. This is more interesting. The last example maybe we can take before we leave. So there's a similar thing. We take a NMOS, connect to 3.3 here. The capacitor is there. Initially it is not charged, 0 volt. At time t equal to 0, I close the switch. What will happen now? So the moment you close the switch, I have 3.3 here, and this is 0. Gate to source voltage is 3.3. And the transistor is in saturation region, starts to charge. Right? As it starts to charge, what happens? Two things are happening now. As it starts to charge, drain to source voltage drops, but in addition to that, VGS also drops. So if I make a simplified view right now, that the transistor, very simplified view, that the transistor will not conduct much current below threshold. So this keeps on charging till what voltage will it charge? It will charge to about 2.3 if the threshold voltage is 1 volt. It will charge to 2.3. And as it charges to 2.3, 3.3 minus 2.3 is 1 volt. It sort of stops there. Right? It charges up to 2.3 and it won't charge further. It would charge because the current, remember the current is not entirely, if you look at IDS versus VGS, it gives a false impression that the current below threshold is 0. The current does flow below threshold, but the current becomes very small. As you keep on going, the current becomes smaller and smaller. So it charges up pretty rapidly till it reaches threshold. Once it reaches threshold, it would charge very, very slowly. And under practical time scales, if I'm talking about a few microseconds and all that, you'll see. So you see how it ends up charging here. Starts from 0, charges up quickly to about 2. We were saying 2.3 or so, charges to 2.27 or so, remains practically on the time scale. On this time scale, it looks practically sort of constant. But it is changing, 2.27 and 2.29. And if you leave it long enough, it will rise. If you wait for, I don't know, hours and all that, it will eventually charge up, right? It will charge up to maybe 3 volt and all that. It will keep on charging, okay? Okay, so that's something that we neglected. You're right. As you are changing the source here, the body is connected to ground, so the source voltage is also rising. Yeah, so VTH is also changing. So that's the other complication that happens. All right, so that's so on your own. What you can do is you can try and see what happens if I take a PMOS for discharging a capacitor and take a PMOS for charging a capacitor. How do the things differ? Instead of NMOS, if I take a PMOS. All right, okay.